When you think of flying, the first thing that probably comes to mind is the majestic airplane cutting through the skies. But what really makes that plane fly? Behind every flight, there's a powerful, intricate machine, the jet engine. A piece of technology that seems almost magical, but in reality, it's a combination of engineering marvels, physics, and a little bit of science fiction. Today, we'll dive into how jet engines work, breaking down the complex process into easy-to-understand parts. Get ready for an exciting journey through the heart of modern aviation. What is a jet engine? A jet engine is a machine that takes in air, compresses it, mixes it with fuel, ignites it, and then expels it at high speeds, generating thrust. But this process isn't as simple as it sounds. The power and efficiency of jet engines are what enable massive airplanes to cruise at altitudes of 35,000 feet and speeds over 500 miles per hour. There are several types of jet engines, but the most common in commercial aviation are turbofan engines. These engines are designed to maximize efficiency, providing the necessary thrust while minimizing fuel consumption and noise. But how exactly do these turbines work? Let's break it down. The basic components of a jet engine. To understand how a jet engine operates, it helps to know the main components. A jet engine consists of 5 basic parts: the air intake, the compressor, the combustion chamber, the turbine, and the exhaust nozzle. Air intake, the front of the engine, where air enters. At high speeds, the intake compresses the air entering the engine. Compressor, a series of spinning blades that increase the pressure of the incoming air. This is crucial because more pressure means more efficient combustion. Combustion chamber, the area where fuel is mixed with the compressed air and ignited. The fuel burns at extremely high temperatures, creating hot gases. Turbine, a set of rotating blades powered by the hot gases from the combustion chamber. These blades extract energy from the gas, which is then used to power the compressor and other parts of the engine. Exhaust nozzle, the final part, where the hot, high-pressure gases are expelled at the back of the engine, generating thrust. Step-by-step breakdown. How jet engines create thrust. Now that we know the basic components, let's look at the step-by-step process of how a jet engine creates thrust. Air intake. Air enters the engine through the intake at the front. In modern engines, the intake often includes a fan. This fan is responsible for drawing in air, and while it may seem like a simple task, it's critical. The air intake and fan create a high-pressure airflow into the engine. The majority of the air bypasses the engine core, flowing around the outside of the compressor. This bypass air contributes to the thrust, making turbofan engines more efficient. Compression stage. The air that enters the engine core is sent to the compressor. This is where the magic begins. The compressor is made up of many spinning blades that gradually compress the air, increasing its pressure. As the air is compressed, its temperature rises. By the time it reaches the combustion chamber, the air is highly pressurized and extremely hot, conditions perfect for combustion. Combustion chamber. Now comes the heart of the engine, the combustion chamber. This is where fuel is added to the compressed air. Fuel is injected into the combustion chamber, where it mixes with the high-pressure air and is ignited. The ignition causes a massive increase in temperature, rapidly expanding the air into a hot, high-pressure gas. This gas pushes through the turbine, creating the force that powers the engine. Turbine stage. The high-pressure gases flow through the turbine, which is connected to the compressor via a shaft. As the gases pass over the turbine blades, they spin the turbine, which in turn powers the compressor. This creates a continuous loop, with the turbine generating enough power to keep the compressor running. The remaining energy in the hot gases is directed out of the engine. Exhaust and thrust. Finally, the exhaust gases exit the engine through the exhaust nozzle. As the gases exit the nozzle at high speed, they create thrust, propelling the aircraft forward. The force of the exhaust gases being expelled pushes the airplane in the opposite direction, in accordance with Newton's third law of motion. For every action, there's an equal and opposite reaction. This is what we call jet propulsion. The engine expels gas at high speed, and the airplane moves in the opposite direction. The science of thrust and efficiency. Jet engines rely on the principle of thrust to propel an airplane forward. But how do we get the most efficient thrust? The key is in the balance of air compression, fuel combustion, and the amount of air bypassing the core of the engine. Turbofan engines are highly efficient because of their bypass ratio. The bypass ratio refers to the amount of air that bypasses the engine core and flows around the outside of the engine. A higher bypass ratio means more air is used to generate thrust, which reduces fuel consumption and noise. These engines are quieter and more fuel efficient than earlier turbojet engines, which had little or no bypass air. Modern developments in jet engine technology. Over the years, jet engine technology has evolved significantly. Today's engines are not just more efficient, they're also more powerful, durable, and environmentally friendly. One of the biggest developments in modern engines is the use of advanced materials. New alloys and composites allow for higher operating temperatures, improving efficiency. Additionally, 3D printing is now being used to create more intricate and precise engine parts, reducing weight and increasing performance. Another development is the incorporation of electric systems. Hybrid engines, which use both traditional combustion and electric propulsion, are being tested for commercial flights. These systems promise to further reduce fuel consumption and carbon emissions, moving us closer to sustainable aviation. Innovations in noise reduction. Another significant challenge for modern jet engines has been the reduction of noise. Jet engines, especially older models, are notoriously loud, and this has led to public concern, particularly around airports. Fortunately, engineers have made impressive strides in reducing the noise produced by jet engines. One of the key strategies is the design of quieter fan blades. New materials and design techniques, such as variable fan blade angles, allow engines to produce less noise during takeoff and landing. Additionally, advancements in the engine nacelle, the casing that surrounds the engine, help dampen noise by shaping airflow and reducing turbulence. As air traffic increases, quieter engines will play an important role in making air travel more pleasant and reducing noise pollution around airports. The role of computational fluid dynamics in engine design. As jet engines have become more sophisticated, so too has the technology used to design and test them. Computational fluid dynamics, CFD, is a powerful tool that engineers use to simulate airflow and combustion processes within an engine. By creating virtual models, engineers can predict how air and fuel behave at various stages of the engine's cycle without the need for physical testing. This technology has drastically shortened design timelines and allowed for more precise engineering. CFD helps improve efficiency, reduce emissions, and optimize fuel consumption, all while ensuring safety. As computational power increases, CFD will continue to play a critical role in the development of next-generation engines, challenges, and future of jet engines. While jet engines have come a long way, there are still challenges to overcome, and one of the biggest is fuel efficiency. Aviation accounts for a significant portion of global carbon emissions, and as air travel continues to grow, the aviation industry is under pressure to find cleaner alternatives. Solutions are on the horizon, though. Researchers are exploring biofuels and synthetic fuels, which are made from renewable resources and can reduce the carbon footprint of aviation. Additionally, the idea of fully electric airplanes is no longer science fiction. Companies are investing in electric propulsion systems that could revolutionize the industry within the next few decades. From the initial intake of air to the final expulsion of hot gases, jet engines are marvels of modern engineering. They operate on principles of physics and chemistry, yet their design continues to evolve. With advancements in materials, fuel technologies, and propulsion systems, the future of jet engines looks promising, both in terms of performance and sustainability. So, the next time you take a flight, remember, you're not just soaring through the sky. You're being propelled by one of the most advanced pieces of machinery ever created, working tirelessly to turn air into thrust. If you enjoyed this deep dive into how jet engines work and want to learn more about the fascinating world of aviation, don't forget to like, comment, and share this video with your friends. We'd love to hear your thoughts and any questions you have about the incredible machines that power our skies. Stay tuned for more exciting content, and as always, keep flying high. The sky's the limit, but thanks to jet engines, we're getting closer every day.